Hi there, grade 10s, and welcome to Learn Extra. In today's lesson, we will be looking at probability. Probability is all about the chances and likelihoods of things happening. Now, when we're dealing with probability, there's a little bit of a new vocabulary that you have to learn, some new words, the meaning of some new words and new symbols. But all in all, it is a section in mathematics that you can do really, really well in. Even if you're not terribly good at algebra, you've just got to have your thinking cap on and make absolutely sure that you understand the language. Right, let's get right to it. During today's lesson, we are going to be looking at the following things. We're going to compare the relative frequency of an experimental outcome with a theoretical event. You'll know more about it just now. We're going to have a look at the probability of something happening, the probability of an outcome. We're also going to have a look at how we can use Venn diagrams to help us in solving probability problems. And then we're going to look at mutually exclusive and complementary events. So hopefully by the end of the lesson, everything that's on this key concept screen will make absolute perfect sense to you. Right, let's go right on ahead. The first thing that we need to know about probability is our probability scale. Now, probability is always a number between 0 and 1. Now, if something is absolutely impossible, we say that the probability of it is 0. If something is absolutely certain, the probability is 1. And everywhere in between, we have certain probabilities. Halfway through, if it's just as likely for something to happen one way or the other, we will say that this is an even chance. For instance, guys, if we throw a coin, we can say that the probability of the coin landing on heads is even chance because it can only be heads or tails. So therefore, it's relatively even chance that, that the probability will be either heads or tail. Right. Now, when we write probabilities, we usually write probability as a fraction. So a fraction between 0 and 1. So we could say a probability of 0,6. Also, though, if you guys watch the weather, you'll hear that they say, oh, there's a 60% chance of rain tomorrow. Remember that a percentage really is also a fraction, so we can also write a probability as a fraction. So very, very important. Probability, we're always dealing with a number between 0 and 1. Not between 0 and 1, it can be from 0, including 0, up to and including 1. And that is if we have an event that is definitely certain. Right. Let's move on and talk about our sample space. Now, the sample space of an experiment is denoted as NS. Now, let's say, for instance, I am throwing a die. Right? What are the possible outcomes that could happen? It could be 1, it could be 2, it could be 3, 4, 5, or 6. So my entire sample space will be 1, 2, 3, 4, 5, and 6. Now, the event is what we call our favorable outcome. So let's say I want to know what is the probability that if I throw a dice, I will get a 2. So I will say the probability of the event of getting a 2 is the number of times that event occurs over the sample space. Now, in a dice, there's a 1 out of 6 chance that I could throw a 2. So the probability of the event throwing a 2 is 1 out of 6. So that is how we write a probability, is the event over the entire sample space, and that will give us the probability of that event actually occurring. Right. Now let's move along to some of the more foreign vocabulary. The first thing that we need to talk about is inclusive events. Now, inclusive events is events that have elements in common. Now, a little bit later on, we're going to deal with a Venn diagram, but I'm going to start by just quickly talking about a Venn diagram in the meantime. So let's say we do a survey at a school, and we ask people, and we find out how many people do biology. So the event of biology will be denoted by a circle. That will show me the sample space of people doing biology. Then at the same school, I find out, well, how many people are there doing maths? And if I find that there are some people in the school, which is highly likely, that do both biology and maths, they will be in this intersection period space between the two, and then we will say that this is an inclusive event. So the two events have elements in common. You can do biology and maths also, and that is what we call an inclusive event, right? So we'll talk a little bit more about the Venn diagrams later on, but just think about it. If you ask a whole lot of people one thing and you ask a whole lot of people another thing, and some of the people can answer yes to both of those questions, then they will be in the intersection of those two circles, and we will say that these are inclusive events. We also then get mutually exclusive events, right? Now, mutually exclusive events are events where there is no intersection. Like, for instance, I can say, if I am pregnant with one child, the child can either be a boy or a girl. If the child is a girl, then it cannot be a boy. If it is a boy, then it cannot be a girl. So that would be a mutually exclusive event. And the definition of a mutually exclusive event, let's write it down. Events that have no elements in common. So the two are really the opposites of each other. Inclusive events are events that do have elements in common. Mutually exclusive events are events that do not have elements in common. Right. Let's move on then to exhaustive events. Now, exhaustive events are such events that together cover all the elements of the sample. So let's say I would to talk about vowels. Let's say my sample deals with the alphabet. So I am looking at the alphabet, and I've spelled it incorrectly. There we go. I'm looking at the alphabet. Now, in the alphabet, there are 26 letters, right? There are 26 letters in the alphabet altogether. And I look at the event of vowels, and I look at the event of consonants. Now, we all know that there are 5 vowels and there are 21 consonants. Now, by looking at the sample space vowels and the sample space consonants, I managed to cover the entire area of the alphabet. So let's have a look quickly at what that means. The probability of a randomly selected letter being a vowel is 5 out of 26. So I want you guys to imagine I take every letter in the alphabet and I put it on a little card and I chuck those cards into a bag and I randomly pick out a card. Now, the probability that I pick out a vowel will be 5 out of 26. The probability that I pick out a consonant will be 21 out of 26. And if I add 5 out of 26 and 21 out of 26 together, I get 26 out of 26, which is 1. And that, boys and girls, is the definition of an exhaustive event. Let's quickly read. 2 elements A and B are said to be exhaustive if together they cover all the elements in the sample. So I'm just going to extend my page a little bit, and we're going to say that the probability of event A or B together is 1, and then I know that, that I'm dealing with an exhaustive event. Right, finally, I'm dealing with complementary events. Now, complementary events are not events that tell you that your hair looks nice. We'll have a look quickly at the mathematical definition of complementary events. So, let's say, for instance, I draw a diagram, a Venn diagram, back to the alphabet, and I start off with the vowels being I, E, I, O, U. Okay, so I, E, I, O, U are the vowels. My diagram deals with the alphabet. What I can say is that the complement of the vowels will be the consonant. So complementary events, for instance, let me just write that nicely. I'll say the probability of a complementary event, and that I denote with a little stripe like that, is 1 minus the probability of the other event. So, for example, we've already said that if I have 2 sample spaces, vowels and consonants, that that together they will give you 1. So I will say, if I have a look at this diagram, the complementary or the complement of the vowels will be everything that is not vowels. And that would be my consonants. So the complementary is the exact opposite, really. That is the word that we can be looking for. So if I say the complement of vowels, what I mean is not vowels. In other words, the consonants. Right, guys, when we do examples later on, I think these concepts will become a little bit more clear to you guys. However, let's just quickly recap. Inclusive events do have events in common. Mutually exclusive events don't have events in common. Exhaustive events, the probability of the one plus the probability of the other gives me 1, and complementary events is everything that is not asked. So in other words, if I say what is the complement of vowels, that'll be the consonants. If I say what is the complement of the consonants, that will be the vowels. Right, guys, let's move along. I have sort of given you guys a little bit of an inkling of Venn diagrams before, but let's do a Venn diagram very, very nicely. I'm going to start off by using all of the numbers. Oh, I'm going to start off by using the first 10 letters of the alphabet, rather. So let's write that down. One, two, three, 4, 5, 6, 7, 8, 9. Okay. So what I'm going to do is I'm now going to put the first 10 letters of the alphabet into a Venn diagram. And I'm going to start by saying my sample space is the first 10 letters of the alphabet. Then my one event is going to be all of the vowels, and my other event is going to be all of the consonants. So we start by drawing a rectangular block. For now, I'm going to let them intersect. That's fine. My first sample space then is vowels, and my second sample space is consonants. Right. In the vowels, I'm going to put A, I'm going to put E, and I'm going to put I. Then in my consonant block, I'm going to put B, C, D, F, G, H, and J. Right. Now, let's have a look at what this Venn diagram means. The first thing that we must notice, and this will not be the case for all Venn diagrams, is that these two events, the event of a vowel and the event of a consonant, is mutually exclusive. How do I know that? Well, I know from my experience of the alphabet that no letter can be a vowel and a consonant. And also, if I look at my Venn diagram, I can see over here that the intersection between the two is actually empty. Now, let's say I ask you, for the complement of the vowels. So, vowel dash. If I ask you for the complement of the vowels, I will close the vowels and I will list all of the things that are not vowels. Okay, so, and if I were to ask you for the complement of the consonants, I will list everything that is not a consonant, in other words, the vowels A, E, and I. Right. Let's then have a look at some other terminology. If I say to you, vowel, and I make it looks like a U, but without the little tail, vowel union consonant. Then I am talking about anything in my Venn diagram that is either a vowel or a consonant. So this union means or. And if I had to highlight the sample space vowel union consonant, let's get a highlighter out here. I will be highlighting everything that's vowel and everything that's consonant, and even if they weren't mutually exclusive events, even if there were some things in the intersection, that would also be highlighted. Right, so this is vowel union consonant. Let's have a look at how I will talk, let's talk quickly about and. So now, if I were to say to you, indicate on your Venn diagram vowel and consonant. The upside down U means and. Now, in this case, because the events are mutually exclusive, we saw before that there was nothing inside the vowels and the consonants. But in a normal Venn diagram, whenever we are talking about and, the part that we are looking at is that part over there where the two things intersect. Right. So guys, that's a little bit of a vocab on Venn diagrams. We're going to be looking at a lot of practical examples just now where we'll be drawing the Venn diagrams and talking a lot about it some more. So it should become clearer to you guys as we carry on. Now let's have a look at our first question. Our first question doesn't necessarily ask us to draw a Venn diagram. Let's have a look. The question says there are 12 white marbles in a box. Each marble is numbered from 1 to 12. A marble is drawn out of the box at random. Calculate the probability of drawing a marble numbered 4. Now, you don't really have to draw the numbers for this. I think this is quite self-explanatory, but let's do it anyway. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. We'll put circles around them so that they look like marbles to us. Now, remember, the probability of me drawing a 4, so the probability that I will draw a 4 is, how many times does a 4 appear? And a 4 appears only once. So let's just divided by all the other possible events, my sample space. So I have got a 1 out of 12 chance of drawing a marble numbered 4. So that's pretty straightforward. Let's have a look at the next question. The next question asks us for the probability of drawing an odd numbered marble. So let's go back to our marbles and have a look. I have got 1, 2, 3, 4, 5, 6 odd numbered marbles. So the probability of me drawing an odd numbered marble is the number of odd numbered marbles, 6, divided by the total sample space, which is 12. And we could write it as 50%, or we could write it as 0,5, or we could just leave the fraction. It doesn't make that much of a difference. Let's have a look at the next question. The next question wants to know about the probability of drawing a prime numbered marble. Now guys, remember, the definition of a prime number is a number that is only divisible by itself and 1. And remember that 1 is not a prime number. So numbers that are only divisible by themselves and 1, let's underline them. 2, 3, 5, 7. Now guys, don't start thinking that all of the odd numbers are necessarily prime numbers. 9 is not a prime number. 9 has got 9 and 1 as factors, but also 3. So my next prime number will be 11, and if I count them up, I have got 1, 2, 3, 4, 5 prime numbers between 1 and 12, or 1 to 12. So the probability of drawing a prime is the number of primes that I have, which is 5, divided by my total sample space, which is 12. Right, now this gets a little bit more interesting. Next question, and this is why I listed the marbles in the beginning, because sometimes it gets a bit hard to just think about it in your head. What is the probability of drawing a prime numbered marble or a marble whose number is a multiple of 4? So guys, the moment we see or, it means I am looking at all of the prime numbered marbles. That's the one thing that I'm looking for an event. I'm also looking for all of the numbers that are multiples of 4. They don't have to be prime numbers and multiples of 4. Right, very, very important. And in fact, boys and girls, you know what I'm going to do? I'm going to draw us a nice Venn diagram based on this. So we are looking for prime numbers or numbers that are multiples of 4. Of 4. Okay. I just think that when it comes to Venn diagram, they didn't say we needed to draw a Venn diagram, but it helps to get as much practice as possible. So let's write down all of the elements of our sample space. That's the numbers 1 to 12. And I write that down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Right. Now, I'm going to start off with a box for my Venn diagram. Let's make it nice and rectangular. Okay, so that's my entire sample space. Will be in there. I'm going to make a circle for prime, and I'm going to make a circle for multiples of 4. I'll call that M4. Okay, Then I'm going to go systematically through my list of numbers. So let's have a look at the number 1. Is it a prime number? No. Is it a multiple of 4? No. So the number 1 has not got a place in the prime number sample space or in the multiple of 4 sample space, so I'm going to put 1 outside. Right. Then I have a look at the number 2 and I say, well, 2 is definitely a prime number, but it's not a multiple of 4 because the first multiple of 4 is 4, of course. So I'm going to put 2 over here in my prime numbers. And let's just cross it out. Next number up is 3, and 3 is definitely a prime number. It's not a multiple of 4, so there goes 3. What's happening with my pen? Right. Next up, I have the number 4, and 4 is the first multiple of 4. Because remember, 4 times 1 is 4, 4 times 2 is 8, 4 times 3 is 12. That's the multiples. So I'm going to put 4 over here in the multiple of 4. 5, again, is a prime number, so that's cool. 5 gets a space in my prime number circle. Next up is the number 6. Now, 6 is not a prime number. It's also not a multiple of 4, so I'm going to put it in the outside area. 7 is a prime number, so 7 gets its space in the circle. 8 is a multiple of 4. 9 is neither a prime number nor a multiple of 4. 10 is neither a prime number nor a multiple of 4. 11 is a prime number. And 12 is a multiple of 4. Now, let's have a look at our Venn diagram over here. So, I have got 1, 2, 3, 4, 5 elements in my prime number sample space. I've got 3 in my multiple of 4 sample space, and I've got 1, 2, 3, 4 that are neither prime numbers nor multiples of 4. Another thing that I can see from this Venn diagram is that up to 12, the event of a prime number and being a multiple of 4, and that would probably be forever, is mutually exclusive. How do I know that it's mutually exclusive? There are no elements in the intersection between these two. So now that I've put everything into a nice Venn diagram, let's have a look again at the question. It wasn't 100% necessary to draw a Venn diagram, but it's so much fun. Right, so the question asks us, what is the probability of drawing a prime numbered marble or a marble whose number is a multiple of 4? Now, it's very, very important that you guys remember from early on that the word or and the U sign go together. U stands for union, and whenever I have or, I am talking about union. And if I go and look at my Venn diagram, it means all of the events in prime and all of the events in multiples of 4. So I have got 1, 2, 3, 4, 5 primes, and then I've got 3 multiples of 4, so that is 8. So the sample space, prime or multiples of 4, is those 2 entire circles, guys. So I have got 8 out of a possible 12. Okay, so let's write that nicely. We'll say the probability of having prime or multiple is 8 out of 12. Right, guys, so this question asked me for what is the probability of getting a prime number or a multiple of 4. What if we were asked what is the probability of getting a prime number and a multiple of 4? Now, if I have a look at my notation, the probability of getting a prime number and a multiple of 4 will have an upside down U like that, and that means and. So that means it has to be a prime number and it has to be a multiple of 4. Now, if we go and have a look at our diagram, There is nothing in the intersection. There is nothing in the intersection area, so therefore the probability of getting a prime number and a multiple of 4 is 0 out of 12, which is, of course, 0, and I can then say that it is impossible. Right, very, very important. The U sign, like there, the union, means I am looking at the colored in parts like that. The intersection, or and, means I am looking at the places where my two diagrams intersect. Now, very important later on also for our calculations, whenever we see union or, we will be adding. And whenever we see intersection or and, we will be multiplying, but we'll get to that a little bit later. Now, guys, I've carried on quite a lot with this question, but at least now we've got the Venn diagram. So, the next question asks me, what is the probability of getting a marble number 13? Well, our marbles only go up to 12, so the probability of getting 13 is absolutely 0. It is impossible. Right. Next up, the question asks me, what is the probability of drawing a marble whose number is a natural number? Now, guys, let's have a look at our sample space. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All of those are natural numbers. So I can say that the probability of a natural number is 12 out of 12, which is then 1, and which makes it a certain event. Certain. So the number 13 was impossible. And getting a natural number is a certain event. Right, guys, that was our first question. We've got a lot more in store for you, but we're going to give you guys a little break. After the break, we'll be doing more Venn diagrams, probability calculations, and just having a whole lot of fun. See you just now. Right, boys and girls, welcome back. Our next question deals with a pack of playing cards. Now, I have noticed often at school that us as teachers sometimes assume that you guys play cards the way we did when we were young, but these days there's so many computer games that everybody doesn't really play cards. So before we get to our first question on cards, I'm just going to talk to you guys about what happens in a pack of cards. Right, guys, in a pack of cards there are 52 cards, right? 52 cards, and those 52 cards are divided into 4 suits. Right, we get the diamonds. They are red. They go from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then Jack, Queen, King, and Ace. So there are 13 diamond cards, right, in my suit of cards. Then there are another 13 spades. You'll see there's a little spade sign. Black cards, same thing. There's 13 of these babies. Then my other suits are clubs. Clubs look like this. There's also 13 of those, and they are black cards. And finally, I have hearts, like this. Right. So we've got 2 red suits. Those are the hearts and the diamonds, and 2 black suits, the spades and the clubs. Now, for those of you that do play cards, we do get jokers in packs of cards, but when we are doing probability, we just deal with the normal 52 cards. So now that you guys have a bit of background, let's have a look at the first question. The first question says, a card is drawn from a pack of 52 cards, joker excluded. Determine the probability of drawing a diamond. Now remember, I said to you guys, there are 13 hearts, 13 diamonds, 13 spades. Now you must please excuse my drawings. And there are 13 clubs, which look a bit like that. So the probability of drawing a diamond, so let's say the probability of a diamond is, how many diamonds are there in a pack of cards? There are 13, and the entire sample space is 52. So the probability of drawing a diamond is 13 out of 52. And if you want, of course, you can simplify that, and that simplifies down to 1 out of 4 because there's the same number of each. And if you wanted to write it as a decimal, you can write 0.25. You could also write 25%. Right. The next question asks us for a jack of clubs. Right. So the jack of clubs, let's have a look if we can find the jack of clubs in this pack of cards. Here's the jack of clubs. It's got the club sign and it's a jack. Now guys, there are 4 jacks in a pack of cards. There are 4 queens, there are 4 kings, there are 4 1s, 4 2s, 4 3s, but there is only 1 jack of clubs out of the 52. So I'm going to say that the probability of a jack of clubs is 1 out of 52 and leave it at that. Right, next question asks for the probability of drawing an ace. Now an ace is that card that has an A on it. Here's an ace. This is the ace of spades. You get an ace in every suit. So you get an ace of spades, you get an ace of clubs, an ace of diamonds, and an ace of hearts. So therefore we have 4 aces in our entire pack of cards. So the probability of drawing an ace is 4 out of 52. Pretty easy as long as you know what's happening in a pack of cards. Of course, that simplifies to 1 out of 13. The next question asks us, what is the probability of drawing a king or a queen? Right. So we spoke about the word or a little bit earlier on, and we said or goes with that sign union. And whenever we are dealing with or, we will be adding. It doesn't have to be a king and a queen. In fact, who can be a king and a queen? It must be either a king or a queen. Now, we have a king in each of our suits. So we've got a king of hearts, a king of diamonds, clubs, and spades. So we've got 4 out of 52 kings plus 4 out of 52 queens. And that gives us 8 out of 52, which is 2 out of 13. Very important, guys. This or goes with union, and if it was a Venn diagram, you would take both circles. Also, or means that we have to add. Right, lovely. The next question asks me, what is the probability of drawing neither a heart or a spade? So neither a heart or a spade means that we want a diamond or a club, right? The diamonds and clubs are neither hearts nor spades, so therefore there are 13 out of 52 diamonds and 13 out of 52 clubs, and that gives me 26 out of 52. That is exactly half of my pack of cards, and that is then 0.5. Right, so a plain probability question without a Venn diagram. You could draw a Venn diagram for all of these, but really not necessary if it's this simple. Let's have a look at something else exciting, another different way in which probability can be asked. Now, the next question I really, really enjoy. The question says a circle is inscribed in a square. That means that the circle is drawn inside a square, as I can see over here. Guys, it doesn't quite look like a circle over here, but let's use our imaginations. So if that's 50 centimeters, this side is also 50 centimeters, 50 centimeters, and of course 50 centimeters at the bottom. So the question says a circle is inscribed in a square of length 50 centimeters. Calculate the probability of choosing a point inside the shaded area rounded off to 4 decimal places. Now guys, the shaded area I would imagine would be the black area over here. So what is the probability if I randomly put my pen down with my eyes completely closed of putting my pen down in that shaded area? Now, the first thing that we need to consider is our entire sample space. Now, our entire sample space is the entire square, right? So let's calculate the area of our square. I will say the area of our square is 50 times 50. I'm dealing in centimeters. And that is 2,500 square centimeters. Now, the area like I've shaded it is the area that is not blotted out by the circle. Now, obviously, I am first going to have to calculate the area of the circle. Now, because this is a square, I can assume that the radius of the circle is 25 centimeters because the diameter from side to side will be 50. Now, let's have a look quickly at the formula for calculating the area of a circle. The area of a circle is pi times radius squared. So pi r squared. So pi times 25 times 25. Now, I've worked that out. That is 1963,5. Now, let's just talk quickly about what we want. Our entire sample space is the big block. We want to know what is the possibility that I will fall into that pink area. Now, I don't know what the pink area is yet, but I can work it out because I know that the entire block is 2,500 centimeters. The shaded area of the circle is 1,963,5. So the area that's not closed up by the circle will be 2,500 minus 1963,5. And that gives me that the top part of my fraction, let's write that in a different color, is 536,5 over the entire area where I could put my pencil down, which is 2,500. Right, so I'm quickly going to do that little division sum, and that gives me an answer of 0,2146, roughly rounded off. So very interesting how we can bring the probability in with all sorts of shapes and things. Right. Let's have a look at our next question, and I want to move on to questions on Venn diagrams because I think that these are really important. Now, in this question, question 6, we are back again to the marbles, and it says there are 12 marbles in a box. Each marble is numbered from 1 to 12. A marble is drawn out of the box at random, and the following events are given. So we could be drawing an even number. We could be drawing an odd number. We could be drawing a number greater than 7, a number less than 5, a natural number less than 7, and a natural number greater than 4. Now, boys and girls, this is not difficult, but I think it's quite a nice exercise also just in your number theory to quickly write down what you think all of these sample spaces are. So think of our numbers 1 to 12. I'm not going to put them down again. Our even numbers from 1 to 12 will be 2, 4, 6, 8, 10, and 12. So I've got them written down there. That's cool. Our odd numbers will then be 1, 3, 5, 7, 9, and 11. Good. Next up, a number greater than 7. Now, guys, if it's a number greater than 7, it does not include 7. It doesn't say greater than or equal to 7. It says greater than 7. So the only numbers greater than 7 are 8, 9, 10, 11, and 12. So let's write those down. 8, 9, 10, 11, and 12. Then a number less than 5. A number less than 5, again, it does not include 5. So that'll be 1, 2, 3, and 4. Then a natural number. Now, guys, all of these numbers are natural numbers, so they're just trying to freak us out here. A natural number less than 7 will be 1, 2, 3, 4, 5, and 6. And then finally, natural numbers greater than 4 will be 5, 6, 7, 8, 9, 10, 11, and 12. Guys, they haven't asked me a question yet. It's not necessary to write this down, but I just thought it might help us a little bit later on. Now, the first question that we are asked is to draw a Venn diagram, very exciting, representing events A and events B. So event A is drawing an even number. Event B is drawing an odd number. Our entire sample space are the numbers from 1 to 12. Let's do that. So we're going to start off with our rectangle. Our sample space is the numbers from 1 to 12. One circle for even, one circle for odd. Now guys, I know that a number can be either odd or even, so you don't really have to make your circles intersect, because I know that these are mutually exclusive events. If a number is even, it can't be odd. If it's odd, it can't be even. But anyway, let's do it. So we're going to say 2, 4, 6, 8, 10 and 12, and 1, 3, 5, 7, 9, and 11. So that is our Venn diagram representing the events A and B. Pretty straightforward. Let's have a look at the next question. The next question asks us to determine A or B. Right, guys? Or I am looking at the union and I'm going to remember to plus. So that means all of the events in A plus all of the events in B. Now, if I have a look back at my Venn diagram, it means everything in even and everything in odd added together. So that would be 6 out of 12 plus 6 out of 12, which is 1. So that's 12 out of 12, which is 1. Let's just make sure. Yes, the probability of drawing A or B will be 1, definitely. Right, let's have a look at our next question. The next question, still dealing with the same issue, talks about the probability of getting A and B. So now it's our U upside down, and we are talking about the intersection. Now, if two events are mutually exclusive, as they are here, there will be no intersection. As we said already, you cannot be odd and even at the same time. So the answer to the next question is the probability of A and B is absolutely 0. Right. The next question asks us to show by using the rules that A and B are mutually exclusive and exhaustive. Right? Show by using the rules that A and B are mutually exclusive and exhaustive. Right, so let's have a look at how we're going to do that. I'm just going to extend our page here. Firstly, I can say that the probability of A or B is equal to 1, right? So probability of A plus the probability of B is equal to 1. And that is how I prove that my events are exhaustive. There is nothing else possible. So I can say, therefore, A and B are exhaustive. They have no elements in common. And we know that because the intersection between the two are empty. They have no elements in common. So very simple to prove that events are exhaustive. The probability of A plus the probability of B, in other words, the union or the OR, must give me 1. Now, let's have a look at how do I prove that events are mutually exclusive. Now, events that are mutually exclusive, I've said if the one thing happens, the other can't. So the intersection between the two is empty. But let's have a look in symbolic form what we have to prove to be true. So for mutually exclusive. What I need to prove is that the probability of A plus the probability of B is equal to the probability of A or B. Now, we've already established that the probability of A or B is 1, right? We've established that. Let's have a look at the probability of A. Now, probability of A is the probability of getting an even number, 6 out of 12, plus the probability of B, 6 out of 12. So I will basically just say that the probability of A plus the probability of B is equal to the probability of A or B. Therefore, they are mutually exclusive. Now, they don't always have to be 1. It will only be 1 if they are also exhaustive. So that's very important to remember. If you get the probability of A or B, and let's say it's 0.9, it means that they're not exhaustive. But if the probability of A plus the probability of B added together also gives you 0.9, then it means that they are mutually exclusive. So events can be exhaustive and mutually exclusive, but they can be mutually exclusive without being exhaustive. That's very, very important, and vice versa. Right, let's have a look at our next question. Still dealing with the very same thing. The question asks us, are events A and B complementary? Verify your answer by using the rule. Now, guys, they are complementary. The reason they are complementary is because they are mutually exclusive and exhaustive. But let's have a look at what I mean in terms of our Venn diagram. If I have a look at everything, if I close up my even numbers, the only thing that I get is my odd numbers. If I close up my odd numbers, the only thing that I get is my even numbers. So the reason that I'm going to use is I'm going to say they are mutually exclusive and exhaustive, so therefore they are complementary. But let's just have a look at the signage that we have to use. We are going to say the probability of A plus the probability of the complement of A is equal to 1. So if I have a look back at my Venn diagram, my probability of A is 6 out of 12. So the probability of getting an even number is 6 out of 12. Plus the probability of getting the complement of A. Now the complement of A means not A. So not even means odd, and that is also 6 out of 12. That gives me 1. So therefore, these events are complementary. But we're still not finished with this question. Lots still to come. Now we are asked to draw a Venn diagram to represent events A and C. So this gets a little bit more interesting. Hopefully, we're going to have some intersection, not just mutually exclusive events. So let's just have a look at what A is. A is an even number, and C is a number greater than 7. Right, so the even numbers, just again quickly, 2, 4, 6, 8, 10, and 12. And the numbers greater than 7, 8, 9, 10, 11, and 12. Let's put that into a Venn diagram. Start off with our rectangle. Ooh, my rectangle has gotten feet. It seems to be moving, right? And there's my rectangle over there. And I'm going to call event A my even numbers. So I'm just going to call this A because that's easier. I know that A stands for even number. Then I'm going to call the other one C, and that stands for numbers greater than 7. Now I'm going to start with the numbers greater than 7. And what I'm going to do is in the intersection between A and C, I'm going to put the numbers greater than 7 that are also even numbers. So what about 8? 8 is an even number. What about 10? 10 is an even number. And what about 12? 12 is an even number as well. Then I'm going to put the other two, that's 9 and 11. Those are now my numbers greater than 7 that are not also even. Now I must just make sure that I don't repeat. Now 8, 10, and 12 are already in my intersection, so I now need to put 2, 4, and 6 over here. Now, if my entire sample space is the numbers from 1 to 12, I've got to remember to put the guys that don't fall into a circle in the rectangle somewhere. So what have we not dealt with? What about 1? 1 is neither even nor a number greater than 7. 2 is an even number, so 2 has been covered. But what about 3? We haven't dealt with 3. Okay, 4 we've covered because 4 is an even number. What about 5? 5 has not been covered. Then 6 is over here, so that's fine. The other number that's not in is 7. Now it's very, very easy just to check quickly. You can just add up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All 12 of my numbers are represented in my Venn diagram. Let's have a look at the first question on this Venn diagram. Right, the first question on my new Venn diagram asks me, what is the probability of selecting A or C? So remember, or goes with union and it goes with plus. So what I need to do is I need to look at all of my events in A and all of my events in C. So all of my events in A and all of my events in C is 1, 2, 3, 4, 5, 6, 7, 8. So that is 8 out of 12. So the probability of A union C, everything that's in A and everything that's in C will be 8 out of 12, which simplifies to 2 out of 3. Lovely. Let's have a look at our next question. We are now asked for the probability of A and C. So now we are looking at the intersection of our Venn diagram. Let's go back to our Venn diagram. And in the intersection of my Venn diagram, I've got 3 elements. So the probability of A and C is 3 out of 12. Very, very straightforward. 3 out of 12, guys, of course, simplifies to 1 out of 4. Right, guys, let's have a look at question I. The question says, show by using the rules that A and C are inclusive but not exhaustive. Now, guys, let's have a look at the exhaustive part first. If it is exhaustive, if my events are exhaustive, the following must be true. The probability of A or B must be equal to 1. If the probability of A or B is equal to 1, then my events are exhaustive. If the probability of A or B is not equal to 1, then my events are not exhaustive. So we can have a look quickly at our Venn diagram again. Right, so we've already calculated that the probability of A union C, that's the probability of A or C, is 8 out of 12. Let's look. 1, 2, 3, 4, 5, 6, 7, 8 elements in A or C. So therefore, my probability of A or C is 8 out of 12. So the probability of A or, and we're actually dealing with C. So let's just write event C, is 8 out of 12, which is not equal to 1, therefore not exhaustive. So very important to prove that events are exhaustive, the probability of A or C, right? When we add the two probabilities, it must be 1. Now, I know immediately that this is not exhaustive because I had elements that are in neither of the two circles. So that already gave me a clue. That would be a perfect verbal explanation. All of my elements are not inside the circles, but we do want the notation. So it's very, very important that you guys remember that. So I've proven now that they are not exhaustive. So let's have a look at how to prove that they are inclusive. Right, so for events to be inclusive, the following, and I do think you guys get this formula, the probability of A union C, so that's or, must be equal to the individual probability of A plus the individual probability of B minus the probability of A, and again I'm using B and we're actually dealing with C, never mind, probability of C minus the probability of A intersection C. Right, so you can do it separately, left hand side, right hand side. I'm going to say I already know that the probability of A or C, because I've just done it, is 8 out of 12, right? 8 out of 12. Now let's have a look at the probability of A plus the probability of C. The probability of A on its own is 6 out of 12. The probability of C on its own is 5 out of 12. And now I need to subtract from that the probability of A intersection C. So let's go back to our Venn diagram and look at those elements of intersection. Do you guys see that I've got 1, 2, 3 out of 12 in the intersection? So back again to my current question. Okay, so this right-hand side gives me 11 over 12 minus 3 over 12, which is 8 over 12. And I can then say the left-hand side is equal to the right-hand side. Therefore, they are inclusive. Right. Just make sure, yes, they are inclusive but not exhaustive. Guys, I'm just quickly going to summarize this for you guys. If you are wanting to prove that events are inclusive, go with left-hand side equals probability of A or B. Calculate that. Then say the right-hand side is the individual probability of the one plus the individual probability of the other minus the probability of the intersection. And if those two things are the same, my events are inclusive. If those things are not the same, then my events are not inclusive. Right, guys, very, very important. Take a note. If the left-hand side and the right-hand side are equal, they're inclusive. If they're not, they're not. And for exhaustive, probability of A plus probability of B must give me 1. If it doesn't, then it's not exhaustive. Right, guys, you might now be exhausted. So we're going to take a short little break before we move on to our next question. Don't go away. Right, guys, welcome back. We're on to our next question. This question is also dealing with the numbers from 1 to 12, so we should be very used to them now. And we start off where we are asked to draw a Venn diagram to represent events C and D. So event C is drawing a number greater than 7, so that's, let's just quickly write that down again. 8, 9, 10, 11, and 12. And D drawing a number less than 5, 1, 2, 3, and 4. Right, so draw a Venn diagram to represent C and D. Doesn't look like it's going to be all that interesting, but let's do it. So there's our Venn diagram, a circle for event C and a circle for event D. Now guys, the first thing that I notice is that event C and D have absolutely no elements in common. D is 1, 2, 3, and 4. C is 8, 9, 10, 11, and 12. So that means that these events are, again, mutually exclusive. Right, so let's put D's elements in. That's 1, 2, 3, and 4. And then the elements of C is 8, 9, 10, 11, and 12. 8, 9, 10, 11, and 12. Now, guys, we have to remember that we are dealing with all of the numbers from 1 to 12. So we've got to make sure that we account for all of them. So I've got 1, 2, 3, and 4. I don't have 5, 6, and 7. So they are going to have to be outside my two circles, but still within my rectangle. So there is my Venn diagram to represent the events C and D. Now again, the next question asks us, determine by using the rules whether C and D are mutually exclusive or inclusive, exhaustive, not exhaustive, complementary, or not complementary. Right, so that's quite a list. I'm going to go back to my Venn diagram and we're going to have a look here. Firstly, guys, let's quickly talk about events being exhaustive. So we've said that if the events are exhaustive, then the probability of C plus the probability of D will equal 1. When will it not be exhaustive? Well, that is if the probability of C plus the probability of D is not equal to 1. So those are our two options. I'm starting with exhaustive because it's the easier one. Let's have a look at the probability of C. 1, 2, 3, 4, 5. 5 out of a possible 12 is 5 out of 12. The probability of D, let's scroll up again, is 4 out of 12. So the probability of C plus the probability of D is 9 out of 12. That is not equal to 1, so they are not exhaustive. Right, so that's my first little thing that I have to deal with. Right, so remember, the one plus the other must be 1 in order for them to be exhaustive. Right, now let's deal with mutually exclusive and inclusive events. Let's make some space. And mutually exclusive and inclusive events. Now, I can actually already see that these two are mutually exclusive because there's no intersection, but let's have a look quickly. For our inclusive events, and I'm going to write down, if they are inclusive, the probability of A or B must equal the individual probability of A plus the individual probability of B minus the probability of A intersection B. So that is for inclusive. So let's have a look. The probability of A or B, that's 1, 2, 3, 4, 5. 5 out of 12. So the probability of A or B, sorry guys, is 1, 2, 3, 4, 5, 6, 7, 8, 9 out of 12. We already know that. It's not necessary to add them together again. So I'm going to say this side is 9 over 12. Then the individual probability of A is 1, 2, 3, 4, 5. 5 out of 12 plus the individual probability of B, 4 out of 12. Minus from that the probability of A intersection B, and of course the probability of A intersection B is nothing. So I can say that these are inclusive. Can you guys see that I will get the same answer on the left-hand side than I will get on the right-hand side? So I'll get 9 out of 12 and 9 out of 12, so therefore they will be inclusive. Let's quickly have a look at the test for mutually exclusive. Mutually exclusive. So if they are mutually exclusive, then the probability of A or B will be equal to the probability of A plus the probability of B. Now we already know that A or B is 9 out of 12, and we've already seen that the probability of A is 5 out of 12 and the probability of B 4 out of 12. So therefore again we have equal left-hand side, right-hand side, so we can say that they are mutually exclusive. Let's have a look at the final question asked us, whether they are complementary or not complementary. So let's get back to our screen with our Venn diagram and we'll have a look at complementary. So I can say that if the probability of not C is the same as 1 minus the probability of C, then the events are complementary. I could have used D as well. So the probability of not C. So let's have a look. Everything that is not in C. Everything that's not in C is 1, 2, 3, 4, 5, 6, 7 out of 12. So we'll fill that in. Then on this side, 1 minus the probability of C. The probability of C is 1, 2, 3, 4, 5. So that's 5 out of 12. So basically what we have here is 12 out of 12 minus 5 out of 12, which is 7 out of 12. So the left-hand side and the right-hand side are equal. So therefore, I can say that these events are complementary. Right, guys, we've dealt a lot now with the numbers between 1 and 12. And I think it's time that we have a look at something a little bit different. The next question is quite different from everything else that we've done because there isn't really a context. We are just given probabilities. So that doesn't mean to say that it's difficult though, so let's have a look. They firstly tell us that G and H are inclusive events. That's very, very important. In a sample space S, it is given that G or H is 3/4. The probability of G or H is 3/4. The probability of G is 2/5. And the probability of H is 1/2. They then ask us to determine the probability of G and H. Now, to start off with, you have to look at the fact that we are told that these are inclusive events, and I'm going to write down what we know for events that are inclusive. I can say that if the events are inclusive, then the probability of G or H must be equal to the probability of G plus the probability of B minus the probability, and here I start with my B's again. This is of course meant to be H, minus the probability of G intersection H. Right. So the reason I'm able to write down this statement is because I was told very clearly that the events are inclusive. Now let's have a look at what information is already given to me. I am told that the probability of G or H is 3/4. So G or H, that's G union H, that's 3/4. I am told that the individual probability of G is 2/5. That the individual probability of H is 1/2. And I'm asked for G and H. And of course, G and H is G intersection H, and this is exactly the bit that I'm looking for. So what I'm going to do now is I'm just going to change around the subject of the equation to solve for G intersection H. So I'm taking the probability of G intersection H to the left-hand side, so it becomes positive, the probability of G intersection H. Then I move the 3/4 to the other side, so that becomes -3/4, negative, so -3/4 plus 2/5 plus 1/2. Right, -2/4 plus 2/5 plus 1/2. And I end up with the probability of G intersection H is 0,15. Guys, so this is completely numeric. Everything deals only with probabilities. I don't even know how many elements there are in G intersection H. However, in the question, not that I really need to use it, they did tell me that my sample size is 20. So what I can do, and that's not asked, but if I wanted to know how many elements is there in G intersection H, I could have said 0,15 times 20, which would have given me 3. So therefore, using the probabilities backwards, I would have been able to say, right, there were 3 elements in the intersection. We were also told the probability of G was 2/5. Now, if the probability of G is 2/5, I can say 2/5 times 20, and that means that there were 8 elements in G, but of course I need to subtract the 5 that are in the 3 that are in the intersection, so that gives me 5. Furthermore, I was told that half are in H rather. So what I can now do is I can say 0,5 or a half multiplied by my sample size of 20 gives me 10. However, there are already 3 in the intersection, so this would be 7. So looking at this Venn diagram, I've just reconstructed it. 5, 3, and 7, my sample size, of course, is 20. So that means that I have another 5 elements floating around outside. So just to recap, the fact that I was told it was inclusive means I could write down this statement. I was given the OR and I was given the individual probabilities. I was then able to change the subject of the equation to calculate the intersection, which I found to be 0,15, and that's fine. The probability is 0,15. The fact, and I could stop the question there, but the fact that I knew that the sample size was 20 means that if I multiplied 0,15 by 20, I got 3, so my intersection is 3. Then I looked at the other probabilities. This one was 2/5. I said 2/5 times 20, and I subtracted the 3, and that gave me the 5. Again, a half times 20 gave me 10, but subtracting the 3, 7 in there, and 5 on the outside. So really quite a lovely question. It could have gone on a lot further. But let's have a look at the rest of the question. The next of the question says to me, determine the probability of getting not G. In other words, the complement of G. So let's go back to this Venn diagram that I've drawn, because actually that makes things a lot easier. So I'm not allowed to include anything that's in G, so I'm going to scratch out G. And let's have a look at what is not in G. Well, I've got the 7 elements in H, which are not in G, and the 5 that are outside. So the probability of G dash or not G, or the complement of G, is 12 out of 20, which I can then simplify to 6 out of 10 or 3 out of 5. Right, so 12 out of 20. Guys, it's very important when you are given a question that is not context-based like this one, where we are just given fractions, to look very carefully about what they tell us about the set of data. They've got to tell us, is it inclusive? They've got to give us information such as that. And it was based on the fact that we were told that we've got an inclusive situation here that I was able to write down that sentence that I wrote down initially. So just let's quickly have a look. If we are told that we are dealing with mutually exclusive, the following can be assumed. The probability of A or B is the same as the probability of A plus the probability of B, because of course there's no intersection. If we are told that we are dealing with inclusive, we can say that the probability of A union B is the same as the probability of A plus the probability of B minus the probability of A intersection B. Right. So very, very important that we look out for those keywords and that we know the definitions that go with them. Boys and girls, Venn diagrams, probability in general, is a new language altogether, but it does get a lot easier the more you practice. So make sure that you guys know the vocabulary and make sure that you draw as many Venn diagrams as possible. I promise you that they do get easier. For now, that's all from us. We'll see you again next time.